Today I'm going to talk to you in more detail about the binomial distribution, specifically the properties of the binomial distribution. So just as a quick reminder, we have the binomial distribution when each of these bullets under the scenario is satisfied. There's a fixed number of trials. Each trial has one or two outcomes, success or failure. Each trial is independent. Each trial has probability of success P, probability of failure 1 minus P, which is called Q, and the random variable counts the number of successes out of the fixed number of trials N. Then we can use the probability distribution f of x written down. And a few properties of the binomial distribution. The first is that the moment generating function is q plus p e to the t to the power of n. The mean, or expected number of successes, is n times p, and the variance is npq. I won't prove property 3, but I will prove property 2 and tell you how you could prove property 3 if you wanted to. So let's prove a few of these things. So let's prove 2. I'm going to use that the expected value of x here, called mu, is just the moment generating function when you take the derivative and evaluate at 0. So we're going to take the moment generating function q plus p e to the t raised to the nth power and evaluate it at t equals 0. Okay. So we need to differentiate that. That involves the chain rule. Since it's to an exponent n, we need to use the chain rule. So we bring that exponent down. We reduce the exponent by 1 and keep the inside the same. But now we multiply by the derivative of the inside. The derivative of q plus p to the t, remember q is a constant, so it goes away. It's just the derivative of p to the t, which is p to the t itself. Evaluated at t equals 0. Okay, let's plug in t equals 0. This will be n times q plus p. Excuse me there. I skipped one thing, times by e to the 0. Remember, e to the 0 was 1. That's to the n minus 1 power, times by p times e to the 0. We're going to use this fact that p plus q is equal to 1, and that more or less comes from the above. Remember, probability of failure is q, and that's 1 minus p. Okay, so this will be n times by 1 to the n minus 1 power times by p times by another 1. And that just reduces to be just n times p. So we proved it. Great. Okay, I'm going to just talk about notes on 3. The variance of x, that's going to be the expected value of x squared minus mu squared. We already know what mu squared is. We just derived it. So that'll be n times p squared. And e of x squared is equal to the second derivative of the moment generating function evaluated at 0, which you'll need to do yourself. Okay, it's not that bad. It's another chain rule and product rule. Okay, so this is for you, and I want to make that little O bigger, and there we go. So that's for you. Dot, dot, dot. Okay, let's prove one. To prove one, we need to use a fact from calculus. And that's a plus b raised to the nth power can be written as the summation from j equals 0 to n of n choose j times by a to the j times by b to the n minus j. Okay, and you can prove that using a Taylor series if you like. I think there's another way, but that's, one of the main ways to prove this fact about this finite series. Okay, so we have that fact, and we need to calculate the moment generating function of a binomial distribution. Its definition is the expected value of e to the tx. We calculate expected values by taking what's inside the expected value e to the tx, multiplying it by the probability density f of x. This will be from x equals 0 to n. And because we know what f of x is for a binomial distribution is given by this formula, we'll just write that formula down. So this will be the summation from x equals 0 to n of e to the t times x times by n choose x times by p to the x times by, I'll write q here, q to the n minus x. Okay. Notice that these two things have the same exponent, so I'm going to combine them. This will be summation x equals 0 to n choose x times by p times e to the t, and they have the same exponent, that's x, times by q to the n minus x. I'm going to call this piece A and this piece B. If I use this fact from calculus, I can find the sum of this series. It's a plus b raised to the nth power. Now, this will be p times e to the t plus b, which is q, raised to the nth power. And there we go. That's exactly what we had listed under the moment generating function for the binomial distribution. So we proved these fun facts, except for 3. I've just told you how you could prove it, and from time to time you could be asked to calculate the mean, the variance, or the moment generating function. Not necessarily derive them, although that could happen as well. So just be prepared to answer questions like, what is the mean of a binomial of this scenario? How many successes should you expect? What's the variation? You might be asked to calculate a mean based on a moment generating function, or even derive one. Okay, thank you.